This is Aerodynamics podcast number 43, and today we're talking about the effects of winglets on the wingtip vortex. To do that, we're going to look at a paper called Experimental Investigation of the Wake and the Wingtip Vortices of a UAV Model. And for those of you who know, when you have any aircraft really with wings, fixed wings, when they are producing lift, you almost certainly get something called a wingtip vortex. And what this is when you have the wing is producing lift, the bottom surface is usually called the pressure surface because that is a higher pressure. The top surface is called a suction surface because that is a higher pressure. The difference between these two surfaces then result at the edge of the wing, so the ends, the tips, this bleed over of air going from the bottom surface to the top surface, so the pressure surface to the suction surface, and creating this vortex, one on each side. And you can actually get a change in vortices. So if you have the bottom surface producing the lift, so the pressure side is now the top and the suction side is the bottom, you then get the reversal of that. So this vortex is really just a manifestation of a change in pressure between the two surfaces. It doesn't matter whether it's the top or bottom or top. And this is important because, as we'll cover, this is a main component of drag for an aircraft, particularly a fixed wing aircraft. It's called induced drag, and we'll cover what that is briefly down below. So this paper is open access, so you can find it in the link in the description if you want to play along at home. Otherwise, I'll go through it here. So they just talk about their paper. They go through a UAV. They're looking at UAVs because of their particular flight paths. And they want to see if winglets will improve the performance of a UAV. And to do that, they're looking at a whole bunch of experimental methodology. They look at smoke wire, they look at a Rayleigh scattering approach, which is where you shine a laser into a system with some sort of seeding particle, and you see what the flow is doing. It will illuminate in the pattern that it's moving in. They're also using LDA. And for LDA, they're looking at the velocities, vorticity, and circulation measurements, which are all really good, especially circulation. That's something that we don't really see too often, mainly because it is a little bit difficult to find. The reason why is because you need to get a really big you need to capture the entire vortex to be able to see the circulation to calculate it. Otherwise, it will be incomplete, your calculation, and it won't be accurate. So they're looking at the circulation, which is good. And the reason why they're looking at UAVs is because they say that there are ideal solutions for a bunch of different applications, such as fire detection, search and rescue, coastline and sea line monitoring, and security surveillance. And one of the major reasons why is because they have no onboard crew, and they have reduced operational costs, and they can fly into hazardous conditions without worrying. Like if a UAV melts or whatever, it's not a huge deal. It's not a person. And so they can have an increased flight endurance because they don't have this additional weight that you need to pilot it. You can get rid of that. So in the case of a UAV, they say, when the endurance is only limited by the available fuel on board, it is essential to be as aerodynamically efficient as possible. For a given mission, the required lift force is already defined. So that means that you already know how much lift you want to produce in the mission profile. So now it's really just a matter of reducing the drag as much as possible to maximize the lift to drag ratio. The lift to drag ratio is a measure of an aircraft's aerodynamic efficiency. The higher this value, the better the aerodynamics is. So a lift to drag ratio of, let's say, 20, which is something you might get on a glider, is really good. For a passenger airliner that you might go on, that's more in the range of about 10. So it's still pretty good, but it's not like glider territory. And for a UAV, you want to get this as high as possible as well, so you don't use as much fuel. You can loiter around in the air, so you have higher endurance, and everything's good. So they say for a UAV that operates in a low subsonic incompressible regime, which is the case for most UAVs that are used for these kind of operations, like search and rescue and whatever. The drag breakdown analysis shows that there are two main components of drag. There's overall the profile drag and then the induced drag. The profile drag can be reduced even more to the skin friction and the pressure drag. So the skin friction is when the flow goes over a surface, there's some sort of resistive force between the fluid and the surface because the surface is bumpy. The pressure drag is anytime you have two surfaces, one front, one back, or they have some component of their area in that direction. the difference in the pressure on those two surfaces will create a resulting force. The easiest way to think of this is if you have a flat plate, you put it into a wind tunnel and you have air hitting, impacting the front of it, then the front is going to see a very high pressure. The back of it is going to see a very low pressure. The difference in those pressures will result in a force. The surface area is also the same, so that's why you get that resulting force. So that's profile drag, and you can reduce this, but in this paper they're looking at the induced drag, which is where the wingtip vortices come in. So the wingtip vortices create, they're effectively just dead energy. You're wasting energy with these things, and that's where induced drag comes from. Anytime you see a vortex on an aircraft producing lift, then that's when you get the induced drag component happening. And depending on the component of the flight path, so if you're taking off or if you're loitering or whatever, the induced drag can range anywhere from only 5% of the drag up to 40 or 50% of the drag. So it's a massive component and it's important to reduce it. And that's why we want to look at how winglets affect the wingtip vortex, and if we can reduce that wingtip vortex strength so we can reduce the induced drag. And that's what they're looking into here. So I have a picture here of the UAV with this wingtip vortex roll-up. It's what you just expect at the wingtips. You have these pressure bleeding over from the high pressure to the low pressure side and creating this vortex. And they go in and say that they looked at 2 different wingtip configurations are used, a wingtip without any winglet and one with a winglet. So another word for a winglet is also a sharklet. So a winglet, because these are flow control devices and they're used on airplanes, the different manufacturers have come up with their own names simply because one manufacturer will take a name and then they'll patent it and say, oh, you can't use that unless you pay us. So then another manufacturer will go, fine, we'll make a slightly different design, call it something different, and it's not the same. So we don't have to use your patent. We can patent it ourselves, and now you have to pay us if you want to use our design. And that's why ones are called winglets and others are called sharklets. So the sharklets are for Airbuses, and the winglets are usually for Boeings. So they have a picture here that also shows the winglet, and it's fairly standard. So first of all, the airfoil profile is what they call a NASA NLF 1015 airfoil profile. And what this is, it's mainly designed to keep the flow as laminar as possible. It also looks very much like a supercritical airfoil, where the trailing edge is a little bit pinched. So that's what that profile is, and it's a 15% thickness ratio compared to the chord. The winglet has an angle of, it's tilted up at an angle of 60 degrees, and it tapers towards the end of it, which is typical of a winglet. And it also has a profile as well. It seems like it keeps this NLF 1015 profile as you go up. And then they have the experimental setup, so they put this UAV into the wind tunnel. Now their blockage ratio, I did a podcast on blockage ratios in podcast number 39. So if you want to look at that and how blockage ratios affect results, you can listen to that podcast. The blockage ratio in this experiment was only 1%, so it's really little. So they didn't have to do any blockage ratio corrections, which they didn't. So that's a really good experiment. And then they had on one side the laser sheet coming in so they can do their Rayleigh scattering, and on the other side they had their LDA probes. LDA stands for laser Doppler anemometry, and what this is you just use lasers to then just track where the particles go. I'm not going to go into it because this is a whole podcast in itself. I have some papers on it actually, so you can look at those if you like. I might do a podcast on LDA in the near future as well because it's an interesting technique. They're using that here. And so the chord of their wing was, the mean aerodynamic chord was 36.5 millimeters. The tip chord was 21 millimeters. The aspect ratio was 8, and the wingspan was 302 millimeters. Now, with the LDA, you point these lasers at different points in your flow, and you measure the velocity at these points, which means that you move this laser in a grid fashion. Now, the more dense the grid pattern is, the higher the resolution of your results. And so what they did here, which is a really good thing, is that they increased the grid density in the location of the vortex. This is in that they can more accurately resolve this vortex and understand what it's doing. This is a really good thing to do if you have the time to do it, because if you refine this grid, it means you have more grid points, which means it takes longer to do. And even if you go, okay, well, I only want to refine it by a factor of 2 in each direction, well, overall, that's a factor of 4, which means that you have to spend almost 4 times the amount of time to do this survey. So the fact that they have refined it here is a really good thing. They also then said that with their LDA measurements, their free stream velocity was 13.2 meters per second. So they gave a Reynolds number of 33,000. And term density was 0.7%. However, for the flow visualization studies, so their smoke and their laser, their Rayleigh scattering, they put the free stream velocity to only 2 meters per second. The reason why is because as you increase the free stream velocity, the smoke will become harder to see. So they wanted to make sure they could see it, so they put it at 2 meters per second. Now we actually make a system that does this, and we can go much higher than that because we've tailored it for that. Anyway, moving on. They have their LDA was taken in 3 different planes. One which was half the chord downstream from the trailing edge, another one which is the full chord, and another one which is 2 times the chord. So that corresponds to 16 millimeters, 32.5, or 30, sorry, 18 millimeters, 36.5, and 73 millimeters downstream, respectively. Each one of these planes will give an indication as to how the vortex is developing as we go downstream. And they have a grid pattern here. It's not that important at the moment. So going to the results, they say for the regular wingtip, at 0 degrees angle of attack, the tip vortex is practically non-existent. This is because the lift production is almost negligible. I looked up this wing, and at this angle of attack, 0 degrees, and at a Reynolds number of 50,000, so 50,000 instead of 33,000, it said that the lift generation was negative a little bit. It was like minus 0.2 or something, so it's not that much, but it's still a little bit. So I don't know why there wasn't any lift being produced here. I looked it up on Airfoil Tools, which is a really nice website. It shows you all the different lift and drag curves for a whole bunch of airfoil profiles, including this one. So I don't know why they had no lift being produced here, but they didn't, they said. And that resulted in no tip vortex, which is true. That shouldn't happen. Then at -5 and 5 degrees, the vortex is more clearly defined. So let's look at the flow vis now. Let's zoom out a little bit. We have on the top, we have from -5 to 15 degrees, just this smoke flow vis around the wingtip. And you can see as you increase the angle of attack, this wingtip vortex becomes stronger and stronger. The smoke really swells up, like twirls around. They also have the Rayleigh scattering approach, which is where you shine a laser into the flow sheet of it, and you can illuminate the flow at one point. And again, as you increase the angle of attack, this vortex becomes stronger and stronger. Now, one thing is this smoke, for those of you who can see this picture, is like this zigzagginess to it. This is because it came from a wire, and as the flow went downstream, it starts to break down. So that's why we get the zigzagginess. By the time it hit the wing, it's already starting to break down. It should be a straight line, but this is aerodynamics. That's what happens. Now they said that at -5 degrees, there was a wingtip vortex, but the opposite sign on the lower surface, because that's now producing negative lift, as I mentioned at the start of the podcast. Then at 10 and 15, this vortex becomes very strong. Moving on, they said that in figure 9 they have other parameters, so let's look at that. Figure 9, the main thing to look at here is the vorticity. So I showed the vorticity in those 3 planes that I mentioned earlier. You know how they had one plane half a chord downstream, then 1 chord, then 2 chords. So 18 millimeters, 36.5, and 73 millimeters downstream. And what it shows at angle of attack of, oh no, sorry, this is at a chord of 1. They have other ones down later which are at those planes, but this is at the plane which is just 1 chord downstream of 5 degrees, 10 degrees, and 15 degrees. And what you can see is vorticity. So the more red a color is, the more vorticity there is. And interestingly, between 10 degrees and 15 degrees, the maximum vorticity is not really that different. In fact, you might even argue at 10 degrees, the maximum vorticity is greater than at 15 degrees. And the reason why they said that is because at 10 degrees, the this profile starts to stall a little bit, and that's true. The its curved slope that I looked at about 10 degrees, the lift starts to plateau, and there's a little bit of stall happening. So that's why 15 degrees, you don't get as greater vorticity, and also you don't get as strong a vortex, generally speaking. But from 5 to 10, you do get a massive increase. Then at in figure 10, this is where we have the three planes, one which is half a chord, one chord, and two chords downstream. This is at a constant angle of attack of 10 degrees. And what you can see here is that the vortex dissipates, so the maximum vorticity reduces from 25.1 to 19.5 as you go downstream, and it also gets bigger, so the vortex just expands. This is just dissipation, it's very normal. Then they plotted the average axial velocity at the vortex core with the angle of attack. And interestingly, at a chord, the plane of 0.5 and 1 chord downstream, so that plane, or those two planes, the minimum axial velocity was significantly greater for even 5 degrees than 10 and 15 degrees. I'm not so sure why. It might be due to some of the stall occurring. It might also be due to resolution. So at these planes, the vortices are very tight, which means that they haven't expanded very much, and trying to measure all the parameters in there at all these different grid points is going to be very difficult. You need to get a very tight grid, and they may not have done that. It may be due to stall as well, I'm not too sure. When you go to 2 planes downstream, all of a sudden now the lowest axial velocity, so in the core of the vortex, is very low now for 15 degrees. And again, that may be due just to the vortex expanding to the point where now they can measure the lowest velocity there, just their grid points happen to find it. I'm not too sure. And then they also plotted the vorticity at these 3 planes, the maximum vorticity. And what they found was, as you increase angle of attack, the vorticity does increase in these vortices up into 10 degrees. At 15 degrees, the maximum is not really that much greater. In fact, it may be even a little bit lower, and that's because of a little bit of stall occurring. So before we go any further, I just want to say to check out everything to Aerodynamics, check out the instrumentation we do. We do the atmosphere hawk, which measures the temperature, barometric pressure, and humidity very accurately. So you can very accurately determine the density of your flow. That's important if you want to get a very good experimental campaign, and you also want to use those results to validate CFD. If you don't do that, the validation process will be off. We also do traverses and PIV. We also do Rayleigh scattering, which is what we went through earlier with these figures here, these green figures. Our system can actually go higher than 2 meters per second, mainly because we've found a smoke system that works for us. It's all in the smoke in terms of how well it carries the light and how well it follows the flow. So we've developed that so we can go much higher. Also check out the courses we do. We do CFD, theory, and experimental, so you can become better in all of these aspects. And also check out the National Aerodynamics Conference. It's a conference every year for aerodynamicists to get together and talk about aerodynamics. So let's go on to how installing a winglet affected the wingtip vortex here. Like I said, in terms of vorticity, the difference is really great in terms of the maximum you see inside the core, and is at least 3 times lower. Sorry, 3 times as low, not 3 times lower, 3 times as low, or 2 times lower, compared to the wing without a winglet. So putting this winglet on dramatically reduced the maximum vorticity in the wingtip vortex. And I have plots here at 5, 10, 15 degrees at 1 chord downstream. And you can see now the wingtip vortex is much smaller, and the maximum vorticity is lower as well. And it's really spread out across the entire wingtip. In fact, there's a secondary structure here, which increases with the angle of attack as well. And I'm not too sure what that is from. They didn't go too much into it as well. I think it needs future work done on it. But it seems like there might be some sort of pressure difference between the actual suction surface of the wing itself and the suction surface of the wingtip. And that pressure change is probably creating some sort of secondary feature here. And then they compared these two wings now. One's without wingtips and one with wingtips. And they say that there is a considerable decrease in the size and magnitude of the wingtip vortex when the winglet device is installed on the tip. They have smoke flow vis showing the difference here. And over the one without a wingtip, which is the left figure, you can see there is a massive twirl of this flow, of this smoke. With a wingtip, which is on the right, this twirl is almost non-existent and is very tight. Now, also something to note is that this wing also is notched at the end. This notch will also affect the wingtip vortex as well. They say that the peak axial vorticity with the winglets is only 35.5% of the peak vorticity without winglets. So a massive reduction, only 1/3. And they have more plots. Now they show with and without the winglets the axial vorticity. And again, with winglets, it's almost gone compared to without winglets. And it's like, as I mentioned, like 1/3 of the magnitude. And finally, they look at the circulation with and without winglets. What they find is that with winglets, the circulation is about 1/5 of that without winglets, which means that the wingtip vortex is now only 20% as strong as without winglets. So they've dramatically reduced that vortex strength, which also means they've reduced the induced drag. So in conclusion, they said that the tip vortex does not appear to have a defined structure until 5 degrees with the winglet, because both wings actually, because at 0 degrees the wings weren't producing any lift. But with the winglet also, there was also a secondary structure that occurred. They said with the winglet installed, the trends resembled those of the winglet removed in terms of increased angle of attack, increased the vortex size, generally speaking, but it was much weaker. It also reshapes this tip vortex into this secondary motion and causes the swirling components and peak vorticity magnitude inside the core to reduce. More specifically, the maximum vorticity magnitude in this study is reduced by a factor of 3 with the winglet installed. So that's the end of this podcast. Make sure to like, subscribe, and share it if you have some friends who may like it as well. Check out Aerodynamics, check out the invitation we do, check out the course we do, and check out the International Conference. It comes from every year for aerodynamics to get together and talk about aerodynamics. See you next podcast. Peace out, amigos.